Hey everybody, welcome back to Hanson Math instructional videos. Today's video regards an introduction to parametric equations. Before we proceed with this video, you might want to make sure that you have paper and pencil so that you can take down some notes. And this particular video is targeted at using the TI-84 graphing calculator. TI-83 should be similar enough. Other calculators, you may have to make some adjustments, but I just want to preface everyone before moving forward that this video is largely driven towards utilizing the TI-84 calculator. Thank you very much, and I hope you enjoy my video. Okay, as we move along here, our introduction problem is going to be based on 4th of July fireworks. As we celebrate here in the good old United States, you may have done and seen problems like this before. A skyrocket is launched and can be modeled by the equation y equals negative 5x squared plus 60x plus 2, where x is time in seconds and y is height measured in feet. Use a graphing utility to find the following. What is the highest point of the rocket's flight path, and when does the rocket hit the ground? Now, if you're familiar with this, grab your TI-83 or TI-84, hit pause and see if you can graph this in your graphing calculator, and unpause when you've got it, and you can see if my solution matches. Or if you want to work alongside with me, you can do that too. So right now I'm going to switch over to my present mode for my TI-84. Okay, as we resume, you will see I have a TI-84 plus virtually on the screen here, and I'm going to type in the equation of our rocket from scratch. Again, if you've already done this, you can confirm, or you can take out your calculator and you can work through this with me. So I'm going to punch in my keys here. First, I pressed y equals. I'm in the y equals screen. And I need to put in a negative 5x squared. Notice that I'm modeling pressing the buttons just like you would, plus 60x plus 2, okay? That was the function we were using to model the height of the rocket. Now I'm going to hit graph and see what happens. Graph. Okay, you can see here it's working. I see a blue line, but that certainly doesn't look like the height of a rocket. So what I'm going to do next is I'm going to hit zoom, and I'm going to arrow down to where it says zoom fit, which is zoom 0. So now I'm on zoom fit, and I'm going to hit enter. And let's see if that is a better look for us. Well, now I can see kind of a parabolic path, but I don't need any of this quadrant 3 stuff because nothing's happening as far as time before 0. So what we're going to do now is we're going to go into window. We're going to hit window and see if we can make it a little bit better. X is time in seconds, so I don't need anything in the negative, so I'm going to change that to 0. X max, this means that we're not looking at anything past 10 seconds. Well, I'd like to see a little bit further, so how about we change that to 15? Some of this is just guesswork. X scale 1 is fine. Y min, again, we don't need anything into the negatives because the rocket can't go underground. So I'm going to arrow down to Y min, make that 0. X max, that would be the height of the rocket. I don't really know, so I'm just going to say, I don't think it's going to go higher than 200 feet. So let's try that. Everything else looks good. So now I'm going to go back to graph. And there is our parabolic flight path of the rocket. Now, if we want to try to answer the questions about what was the height of the rocket's flight path. We can do that so we can hit trace and we can answer some questions about this. We can see how high did the rocket go? Okay. The highest it gets is, we could get closer doing max and things like that. But for the sake of this video, it's somewhere in the neighborhood of 181, 182 feet. And we could also say, when does it hit the ground? Well, we can trace over to where it looks like it hits the x-axis here, which would be here we're at 6 feet. Here we are at -7/10. So it's pretty close to that. So it looks like the rocket hits the ground at approximately 12 seconds. Okay. So we can answer questions like that. The rocket hits the ground at approximately 12 seconds. This is, the peak height of the rocket. But what we cannot answer, and this is going to become important, we can't answer anything about how far away did the rocket land from where it was launched. That would be like the horizontal ground distance. See, that is not apparent from this type of modeling, okay, using an equation in our rectangular or Cartesian coordinate system. So now let's move on and think about, what if we wanted more information here? What if we wanted time as the rocket starts from 0 and then, hits the ground somewhere around 12 seconds? What if we want to keep the height information? How high did the rocket go? But what if we also want to be able to see on the same graph, how far away did the rocket land compared to where it started? Well, we have to do some different kind of mathematics to figure that out. All right, now we're going to look at this from more of a trigonometry and physics perspective. So we have the good old skyrocket here, and we're going to have a launch here at the recommended 75-degree angle. And the head of the rocket is 2 feet off the ground because, the ground is going to be where the kind of stick is from whatever you're shooting it out of here. It looks like we're shooting it out of a pipe. So the head of the rocket here is 2 feet off the ground, and the initial velocity is 60 feet per second. Okay. What are the horizontal and vertical components of this? All right, now the first thing I'll preface this by is I am not a physics major, so if I have any errors here, I apologize. This is not a lesson in physics as it is an application of mathematical equations. So let's do the following. Let's take this skyrocket and I'm going to make it into a right triangle. Okay, so here is our 90-degree angle. And we know we're going to fire this at an angle of 75 degrees. And we know the initial velocity, the velocity vector, which I can call V naught. Naught means initial. So we're going to say that the velocity vector is 60 feet per second. And what we don't know, but we want to know, is what is the horizontal or x naught component of the velocity and what is the vertical velocity component, y naught, in the vertical direction. Okay, so you might be able to figure out how we can find these components. We have to go back to good old right triangle trig. This here, this x piece is the adjacent because it connects our reference angle to the 90-degree. And this vertical piece here is the opposite. So we need cosine and sine. All right. So let's start with cosine. The cosine from the 75-degree angle is equal to adjacent, which is the x component, over the hypotenuse. The hypotenuse was 60 feet per second velocity. So we're just going to call that 60, okay? So now to get x by itself, multiply both sides by 60. All right, cross that out. Take your graphing calculator, press 60 times cosine 75. We will round to the nearest tenth, which is probably not good enough for rocket science, haha, but good enough for our purposes. So 60 times cos 75 should be approximately 15.5 rounded to the nearest tenth. All right. So that is our x component. Now to find the y component, let's do the sine of 75 degrees. Well, sine is opposite over hypotenuse. So from here, the opposite is the y component over 60. Multiply both sides by 60. That cancels. So we have y equals whatever in the heck 60 times sine 75 is. If you do it, you get rounded to the nearest tenth. You're right about at 58. Okay, so now we found the components of the vector, the horizontal and vertical components. So what we're going to do is the following. Okay, we are looking for distance. Okay, we want to know how high did the rocket go. We want to know how far from the original point did the rocket land. So what we want to look at is as follows. We have x is going to equal the x naught, which means the original horizontal start, if you will, plus what is distance? Distance is velocity times time. So we're going to have the velocity of x naught times time, okay? Velocity times time is distance. So we have x equals, x naught here is 0 because there was no displacement to start off with. It started at a distance of 0. It didn't go anywhere. Plus the x or horizontal velocity component was 15.5 t. Simplified, the 0 doesn't do anything. It's just 15.5 t. That is our x distance equation. Okay? Now, what about y? Well, we can say that y is equal to y naught, which is the starting horizontal position, plus, again, we want distance, so that's velocity times time. But if we just look at the vertical component, if you were to shoot a rocket, it would go up forever. The only thing that's bringing it down is gravity. So we have to add in the gravity part of the equation, which is 1/2 times negative 9.8. You might understand that if you've taken physics, 9.8 meters per second squared. The acceleration due to gravity, negative because it's pulling it down, times t squared. All right. So now if we plug in for this, we have y equals, the y naught here is not 0. Remember, the rocket started 2 feet off the ground, right? Because the head is off the ground. So that was 2 plus the initial velocity in the y or vertical realm was 58. So we've got 58 times t plus 1/2 times negative 9.8. Half of negative 9.8 is negative 4.9 t squared. Okay. Now, if I take that and rewrite it so that it looks more familiar, we put the highest power, the degree first. So that's going to be a negative 4.9 t squared plus 58t plus 2. That is our y, or vertical distance equation. All right. So let's parlay these together and see where it leads us. What we've developed here, based on the work we did on the last slide, is what's known as a parametric model. So we have a pair of parametric equations. So the parameter here is known as time, okay? So it's like the third variable. We have x, y, and t. So we have time. Everything, the whole model is going to be generated based on time in seconds. That's called the parameter. X is going to give us the horizontal distance in terms of time. So x equals 15.5 t. And then y is the vertical distance equation in terms of time. Y equals negative 4.9 t squared plus 58 t plus 2. So this is a pair of equations. These work in tandem. That's how parametric equations work. It's a pair. And you have x and y in terms of t. T is the parameter. So now I am going to switch over to the TI-84 emulator, and I'm going to show you guys for perhaps the first time ever how you can graph a pair of parametric equations. Okay, now you can see my TI-84 screen, and this is right where we left off prior. So I'm going to do the following. I'm going to click on y equals, and I'm going to clear out that function, which was our parabola in rectangular or Cartesian coordinates. And now we're going to switch over to parametrics. So this is how it's done. Click on the mode button right here on your calculator, mode. So click mode. And normal's fine, float's fine. You want to be in degrees, so make sure you're in degrees. But now you want to go down to the line that says function and then parametric next to it. So you arrow over so that your blinker is flashing on parametric, and then you want to go down and hit enter. So now you are in parametric mode. Okay? Once you are in parametric mode, I want you to click y equals once again. And now you can see there was some stuff loaded into my calculator. There may be in yours, there may not be. I'm going to clear these out. So I hit clear. Now I have to arrow down to get to the y equation and hit clear, and then go back up. Okay, so my blinker is on x sub 1 in terms of t. That's our x equation that we just worked on for the skyrocket. Okay, if you recall, that was 15.5 t. So it's 15.5, and your t is the same button. It's shared with x. It's x, t, and theta. It could be any of those. So you click that button that you can see my mouse on, and that puts in our t. When you're done with that equation, which we are, you hit the down arrow. Now you're in the equation of y in terms of the t time parameter. And that one was negative 4.9 t squared plus 58 t plus 2. Okay? So we've loaded in the equations, one for x, one for y. We're ready to graph this sucker, but first we want to go to window. To me, this is one of the most important aspects of parametrics. Click on the window, which is up top. It's in your top row next to the y equals. Click window, and let me walk you through the different things here. T min is the time parameter. So we're going to start with 0. That's good because we're starting at 0 seconds because the rocket hasn't been fired off yet. Now I'm going to click down. T max means what's the maximum time we want to go to? Well, I'm going to take a guess that the rocket probably wasn't in the air for more than 30 seconds. So I'm going to change this to 30 seconds, 30. T step is what you want the time change increment to be. I'm thinking let's be able to look at this in half-second steps. So I'm going to change that to 0.5. Going down, x min, remember x would be distance. So 0 would be starting right at where you shot the rocket. That's fine. X max would be how far did it go? I'm going to guess 300, no more than 300 feet. So I'm going to put in 300. X scale, you can leave at 1. Y min, again, this is height. So the ground would be 0, so that's fine because the rocket was only 2 feet up, so 0 is fine. Y max, again, would be how high did the rocket go? Again, I'm going to guess, let's say that I don't think it went any more than 300 feet. So I hit 300. Y scale, you can leave at 1. Okay? So with these assumptions, I'm going to go back and hit graph, and let's see what it looks like. Well, yeehaw! There is the flight path of the rocket. Now, you can see that there's some dead space up top and there's some dead space to the right. So I'm going to go back into window real quick, and I'm going to decrease the X max. So I'm going to hit down, down, down. I'm going to decrease X max to 200. Again, that's a guess. And I'm going to decrease Y max to 200 just to see if the graph fills up more of the window. I'm going to hit graph. Okay. To me, that looks beautiful. None of it's clipped off. I can see the entirety of the curve. So now we're going to hit trace. Remember, trace is in the top row. Trace. And you can see the blinker here. At a time of 0, it has not gone horizontally. That's a distance of 0. But it has gone a vertical distance of 2 because that's where the head of the rocket was, 2 feet off the ground. Now, if you start clicking the right arrow, you can see we're going to go in half-second increments. All right, so if I stop here at 2 seconds, after 2 seconds of the rocket being shot off, it traveled 31 feet ground distance, and it's 98.4 feet high off the ground. This literally is the flight path. You're not looking just at height now, you're looking at 2 quantities. You can see both the horizontal distance traveled and the vertical, which is pretty cool. Now, if we keep clicking the right cursor to keep tracing, we can see approximately how high this sucker went. It went about 173 feet high at its zenith or peak. And it was at that point, if you trace this down to the ground, it was about 93 feet away from where you started. Okay, how cool is that? Now, if you keep going, again, you can stop wherever you want. At 10 seconds into its flight, okay, you can clearly see it's on the way down to hit the ground. Now it's 155 feet away from where you lit it off, and it's still 92 feet in the air, then all the way until it crashes into the ground, which would be somewhere, again, we can't have negative here, would be below ground, but it's somewhere around 12 seconds, and you're going to have to walk 186 feet from where you started if you want to pick up the rocket to discard it. So here you go. Here is the first real-life example we've looked at with parametric equations. We're going to look at one more example that many of you will be familiar with, and then wrap this video up for today. Okay, thank you very much. Here comes example 2. Okay, what we're going to do here is something called parameterize. Easy for me to say. We're going to parameterize the unit circle, which means we're going to change it into a parametric equation. So here is our rectangular system, x squared plus y squared equals 1. And now we're going to do a substitution. We know how to find x on the unit circle, that's cosine. We know how to find y on the unit circle, that is sine. So what if I wrote down sine squared x plus, actually, you know what, if I'm being consistent, that should be cosine. Okay. Cosine squared x plus sine squared y equals 1. If you remember doing trig identities, that is called the Pythagorean identity, right? This is basically an even exchange. You can swap out x with cosine, you can switch out y with sine, it still equals 1. This is the Pythagorean identity. These two are synonymous. It's an even exchange. So now what I'm going to do is the following. I'm going to take just this equivalence right here, and I'm going to write that out because it's true, okay? X squared is the same thing as cosine squared x, and y squared is the same as sine squared y, okay, if you're looking at these in terms of equivalent components. So now, what happens if we solve this for x? You take the square root of both sides. So the square root of x squared is just x. The square root of cosine squared is just cosine, okay? And actually what I'm going to do is I'm going to change from x, I'm going to change to theta, because after all, in the unit circle, we're going to be looking for the angle. And what if we do that over here as well? I take the square root of both sides, so we have y equals, the square root of sine squared is just sine, but now I'm going to change it to theta. Okay, sorry about that. Hopefully that's not, doesn't throw you off too much. So now, wouldn't you know, this looks really familiar. We have x equals cosine theta and y equals sine theta. Okay, so what happens if we graph these as a pair of parametric equations and our parameter is theta? So not only can your parameter be time, your parameter can also be theta, which is an angle. So let's go back to the TI-84 and let's take a look. Back on the TI-84 graphing utility, you can see that I still have the x and y equation for the skyrocket problem that we did. So I'm going to clear that out, clear, cursor down, clear. And in x1, I am going to enter the cosine equation, which was cosine theta. Again, the calculator is going to put in t because that's what it does in parametric mode, but it's just a variable. You can think of it as theta. And I cursor down, and for y, I'm going to put in sine, and then my variable, which again is xt theta. The calculator defaults to t for parametrics. Now, before we hit graph, we want to hit window, and let's think about how the unit circle behaves. So let's start with thinking about degrees, because the last I checked, my calculator was in degree mode. So T-min would start with 0 degrees. That makes sense. Go down, and let's make it go 360, which is 1 full revolution. T-step, that's half a degree right now. 1 degree seems kind of small. That would be okay. How about we'll have, when we hit trace, it'll move in 15-degree increments, which is pretty good. And again, since it's the unit circle, the x goes from -1 to +1, and same thing for the y, -1 to +1. That should look pretty good. Let's hit graph. And, it looks like an ellipse. I thought this was a circle. Well, it is. The display on your screen, the pixels are wider than they are tall. So to compensate for that, you need to hit zoom, which is in the top row, and square, which is option 5. Zoom square compensates for the rectangular array of your screen and makes it look correct. So now we are in good shape. If you hit the trace button in the top row, you'll notice that your blinker starts right here, which means at 0 degrees, your coordinates are 1, 0, which is correct for the unit circle. Now, you can hit the right cursor and move all the way around, and since we put it in 15-degree increments, it works really well. So you can see here at 30 degrees, you're at 0.866, which is √3/2, and your y value is 1/2, which is correct at 30 degrees. 45 degrees, these 0.707s, those are your √2/2s. Your 60 degree is your 1/2 and your √3/2. And then you can go on into the negative side and keep going. And it gives you all your unit circle values beautifully. They're just in decimal approximations instead of exact value radicals. Now, notice that you can hear me clicking like a madman. It's not going to go past 360 because that is the cutoff I put when I was in window. Okay, this all works very, very well. It does make logical, intuitive sense if you think about it. And before we depart here, let me show you what you can do if you want to change from degrees to radians. So go back to mode, click mode, cursor down to radians. Radians is blinking, click enter. All right, now you might want to hit graph, but I'm really telling you, you shouldn't. Click on window. Now let's think in terms of radians. So we want to go from 0 to 2 pi. So I'm literally going to click 2 and then pi. Pi is in the blue above the up caret, above the divide. So I hit second caret. There's my 2 pi. Now my step, let's do, what if we tried pi over 4? So I'm going to do pi divided by 4. So it's going to move in pi over 4 steps. And then the x min should be -1. X max would be 1. Again, for the unit circle, that's all it encompasses. Boom. Now, if we hit graph, what in the heck? I wanted a circle. This is a octagon. Well, the reason for this is I only told it, if I hit trace, I only told it to do pi over 4 or 45-degree steps. So there's only going to be that many data points. Okay, so again, this is why I'm going through this with you guys. I knew that would happen. Hit window. You need more data points. That would be the T step. So I'm going to go down, and instead of pi over 4, what if we did like pi over 16? Okay, that would give us 4 times as many data points. Now if we hit graph, it's a much smoother looking circle. And again, how do you make it look more correctly circular? That would be zoom 5. Zoom 5 is standard, or square, I mean. Zoom 5 is square. It's getting late, ladies and gentlemen. And there is your unit circle. So if you hit trace and go around, it's just the decimal version. You know, like pi is 3.14. There you are at -1. And this is a round off here, that's 0. You can go down to 270 degrees, which, you know, approximately it's 4.7 in decimals. And 2 pi, you know, is approximately 6.28. So there you go. You can do it. I showed you how to look at it in either radians or degrees. That concludes this Hansen math video. If you like this video, please consider clicking the thumbs up like button. And there'll be videos like this, surely a lot more to come, and plus old ones in the archive. Consider subscribing to Hansen Math. And thank you so much for watching. I hope you got something out of this introduction to parametric equations. I hope everyone has a great day, and I'll see you down the road.